Hello, folks. Welcome back. Video lecture 21. Almost there. Next to the last one is our final week of content, of new stuff for the class. Um, so just want to throw out a couple of, suggestions, hopefully get you on into the right path here. Um, uh, Especially during this final week, right? Like we want to be able to prep for our final assessments. The way to do that is making sure that you are efficient in completing your work for this week. So please, as soon as this video lecture is over, go to your homework and do all of the topics that you can based on this video lecture. It'd be super important. Um, Additionally, right, everybody that's watching this video wants to do well in the final assessments. If you want to do that, we need to prepare productively, and really we need to start now. Okay. Preparation starts with one single problem. You do one problem, and that's how you start your preparation. So just start small, start with one problem, and start now. Okay. All right. So today's video lecture, we're talking about simplifying radicals. And as we get to that, I always want to make sure that people conceptually understand what this thing is talking about. So that way it can lead us to a question that kind of guides us. So when we're talking about a radical, we can also call it a root. What is that thing asking? So our most basic radical is kind of like the one that we're used to, is a square root. And so if I'm tasking you with thinking about the square root of 25, what does that mean? So when we ask about the square root of 25, that is asking what got multiplied by itself to arrive at this 25. Another way of thinking about that is what got squared to get me 25, right? And the answer there is 5, okay? Because 5 times 5 arrives at this 25. So for a while now, right, we've become interested in exponents and thinking about how those work. Now we're going to shift the thinking and kind of working backwards, right? We're coming up with a thing that got raised to the exponent that arrives at this radical or this root. So square root, we can also see different types of radicals. We can see a cube root. So if I say cube root of 27, so where a square root was asking what got squared to arrive at 25, a cube root's going to ask what got cubed, right? What got multiplied by itself 3 times to arrive at this 27. So what we can do with radicals is we can change this number, and it's called an index. And you'll see your index written right inside that little crevice there of the radical, okay? So we can have square roots, we got cube roots, we can really have any type of root. You might see some fourth roots, you might see some fifth roots. And so all of these are asking a very similar question. It's just changing like what exponent are we interested in asking ourselves about. So square root is asking about squared, cube root is asking about cubed, fifth root would be asking what got raised to the fifth power. Okay. So let's finish out this one. Cube root is 27. What got multiplied by itself 3 times to arrive at 27? That would be a 3, because 3 times 3 times 3 equals 27. Or another way of writing that is 3 to the third equals 27. Okay. So to accomplish these problems that we're going to do is, we're going to be taking square roots predominantly and cube roots. Those are really the two of the focus here. To simplify square roots, we need to know these ones that work out really nicely. So 25 is a special number because when we take the square root of it, it works out nicely. Those are called perfect squares. So you need to know, like, what is a perfect square and how can I come up with it? Perfect squares are these numbers that if I take the square root of them, they arrive at a positive whole number when the square root's taken. It's made from a perfect square, right? If I made a 5 by 5 square, it would have an area of 25. So the way you can make that list, right, is 2 times 2 is 4. So 4 is a perfect square, 3 times 3, 4 times 4, 5 times 5, 6 times 6. So you need to be able to make this list when you need to, right? 9 times 9, 10 times 10, okay? And you could keep going on. So perfect squares we're going to use a lot, and then we also will be using perfect cubes. So we're going to need to know those as well, or at least be able to come up with a list, right? And this list doesn't need to be very long. So 2 times 2 times 2 is 8, 3 times 3 times 3 is 27, and 4 times 4 times 4 is 64. And honestly, that's probably about as far as you need to be able to go. Perfect cube list gets large very, very quickly. Okay, so we had a couple examples where these were already perfect square, perfect cube. We're good to go. As we look at our first example here that we're going to talk about, we have the square root of 18. 18 is not on our list. If you were to type the square root of 18 into your calculator, it would tell you it's, 4 point something because it's just above 16. So it is this, if you were to type in the calculator, that decimal actually never stops. It's not in repeating. So you never be able to capture the whole entire thing. So what we do is we do our best to simplify it. And the way we will simplify the square roots that, don't come out as this single whole number is we're going to work to break this number apart using a perfect square, since we're talking about square root. Okay, so we're going to ask, what is the largest, and this is the question you should be writing down your notes, what is the largest perfect square that will divide 18? Okay, and divide it evenly. So as we look through our perfect square list, right, we're at an 18, so we might start with just testing 16. Does 16 go into 18 evenly? No. So then we hop down our list. 9 does work. 18 is 9 times 2. So what we're going to do is we're going to rewrite this 18 as 9 times 2. Okay? And then what we can do from there is we're actually able to split these apart if you would like to write them as separate square roots. Okay? And now one of these you can take the square root of, which is beautiful. Square root of 9 is 3. And the square root of 2 is not a perfect number, so we are simply going to leave it as square root of 2. Okay, that is how we will simplify these radicals. We are on the search for the largest perfect square that goes into this number, so we're going to be able to simplify that a little bit, but there will be another chunk left that's not going to be able to be simplified any further, which is fine, but that's our task here. Okay, all right, so let's move on to 72. Yes, so 72. Maybe try it out on your own, right? We're looking for the largest perfect square that goes into 72. So 72, right? 64 doesn't work. 49 doesn't work. 36, 72 is the same thing as 36 times 2. So we can break this apart into 36 times 2. Now, one of those we can take the square root of, so we get a 6. Square root of 2, not a great number, so we're going to leave it as square root of 2. Okay, let's try a few more. 125. So what perfect square goes into 125? And again, I encourage you to pause this and try any of these out on your own. Start to use your instincts here, right? What goes into 125? It ends in a 5. We know that 25 goes into 125. We're not going to find a larger one. 25 times 5 is 125. The square root of 25 is just the number 5. Square root of 5 does not simplify any further, so we leave it right like that. Okay. All right, next one up is a fraction. I want to break this one down real quickly, right? It's asking what got squared to get me 4/25. So what fraction got squared to give me 4/25? And I want to revisit our power rule, right? We know that we're going to square this top number, we're going to square this bottom number. So what got squared to get 4 and what got squared to get 25? Don't let this fraction, eat you up. So, you can think about it in several different ways. Just like we broke up the radical above, you can break up the radical into the numerator and the denominator. The square root of 4 is 2. That's a nice one. And the square root of 25 is 5. And let's test it, right? If I took 2/5 and I multiplied it by 2/5, 2 times 2 is 4, and 5 times 5 is 25. That is our answer. Okay. So another one, we've got 12/27. So let's go ahead and write our radicals. We got radical 12, radical 27. All right, is either 12 or 27 a perfect square? No. So let's do our work of breaking these up. So what perfect square goes into 12? And we want the largest one that divides it evenly, and that's going to be a 4. So we can break up this top as 4 times 3. In the denominator, what is the largest perfect square that goes into 27? It's 9 times 3. So we're going to write a 9. We're going to write a 3. Okay. Simplify this a little bit. I'm going to move this over. So on top, square root of 4 is a 2, and when square root of 3 does not simplify. On the bottom, square root of 9 is 3, and then square root of 3 does not simplify. Okay, so we got that. What do we notice? We have a square root of 3 and a square root of 3 in the numerator and the denominator. Those two things make 1, right? Square root of 3 divided by itself will just be a 1. We often say that those cancel out. So if those cancel out, our final answer is 2/3. That, what we ended with there, is much nicer looking than what we started. Okay. All right. Next one, we're looking at a cube root this time. So we're asking ourselves, what got cubed, right? What got cubed to arrive at -8? Now, what I want you to think about, right, is it's getting multiplied by itself 3 times, and we want to arrive at a negative. If we want to arrive at a negative after multiplying by itself 3 times, our original thing needs to be a negative. Okay, so now just think about, how did we get 8? Right, 8 was actually in our perfect cube list. Perfect cube of 8 came from 2 times 2 times 2. So if we want to come up with a -8, that would be a -2. Let's test it, right? -2 times -2 times -2. Negative times a negative times a negative will work out to be a negative, and 2 times 2 times 2 is 8. Okay. All right, a couple more. Cube root of 216. So now this is asking what got cubed to arrive at 216. Okay. So just a heads up, with a perfect, your perfect cubes list, right? We said 2, or wait, not 2, 8, 27, 64. So that was 4 times 4 times 4, 5 times 5 times 5 is 125. And if we keep going, 6 times 6 times 6 is 216. Okay, so 216 is actually a perfect cube. It comes from 6 times 6 times 6. Thus, our answer here is just the number 6. Okay. All right, so now we're going to venture into some variable territory. So the first thing I want to think about, right, is this first one. It's asking, what is the square root of v to 10th? So a reminder, right, this is asking what got squared to arrive at v to the 10th. So v to some power got squared, and it equals v to the 10th. To do this, right, we have to remind ourselves is, what is our power rule, right? What do we get to do to the powers when we have a power raised to another power? And it's, we get to multiply them. So basically this is just asking what times 2 arrives at 10. And that would be a 5, right? V to the 5th squared equals v to the 10th. Okay. I want us to notice this pattern, right? When we're square rooting a power, what happened to this power? It went from a 10 to a 5. Just got divided by 2. It got cut in half. So whereas when we're squaring, right, we're multiplying by 2, a square root is going to cut this power in half. It's dividing by 2. It's doing the opposite. Okay. So it's a really nice pattern to be able to notice. All right. So we've got another one. So we've got square root of 9 x to the 36th. Just like we continue to do, we're going to look at these two things separately, right? We've got a 9. Let's do the square root of that. And then we got x to the 36. Let's take the square root of that. So if you want to, you can write these separately and then just work with each of them. So square root of 9 is a 3. And then the square root of 36. So it's asking what got squared to arrive at an x to the 36th. And so x to what power got squared, right? And our power rule is getting multiplied by 2 to arrive at a 36. So we get to just cut this thing in half. So x to the 18th, because x to the 18th times itself times x to the 18th would arrive. We get to do 18 plus 18 to get to 36. Okay. Couple more, and we'll be out of here. All right, cube root this time. So we got an index of 3, right? Index of 3. So we're asking what got cubed. So let's break it apart. Cube root of 8 and cube root of y to the 6th. So cube root of 8, what got cubed to arrive at 8? 2 times 2 times 2. And then if a square root, right, is asking what got squared, and we get to cut powers in half, a cube root is asking y to what power got multiplied by 3, right, to arrive at y to the 6th. So instead of multiplying by 3, we get to think of it backwards. We're dividing by 3. This would be y to the 2nd, right? Y to the 2nd raised to the 3rd would equal y to the 6th. Okay, so this right here. All right, one final question, I believe. Yep. All right, so 5th root this time. So we have an index of 5. So we're going to be thinking about the opposite of a 5th power, right? Well, it got multiplied by itself 5 times. All right, so let's go ahead and break it apart. 5th root of 243 and 5th root of x to the 20th. All right, so let's go for this. I want you to go ahead and get your calculator out. Go on a search. What got multiplied by itself 5 times to get to 243? Good clue here, right? It ends in a 3. What number can, when multiplied, can make something end in a 3? 3. 3 to the 5th power equals 243. So this right here is a 3. And now the 5th root of x to the 5th. So it's asking what got raised to the 5th power to arrive at x to the 20th, right? And we would be multiplying by 5. So thus, if we're working backwards, we're going to divide by 5. That would be x to the 4th. 20 divided by that 5 gives us x to the 4th. Okay. All right. Great job. Again, go work on some topics for this week. Be efficient, be productive. One question before you get to class. I want you to try out this one, okay? So we're simplifying the square root of 75z to the 22nd. All right, great job. I'll see you back for your last video lecture of Math 122.